Well, good morning and happy Friday. Okay, so let's return to absorption. We left off with this slide here, and we defined a number of terms, including the number of transfer units. And one of the things to think about here is the smaller the denominator in the number of transfer unit equation, the larger the number of transfer units needed. So Y star is an equilibrium concentration. So the smaller the difference between the actual concentration and the equilibrium concentration, the larger the number of transfer units you need, which means you need a taller column or deeper column. The height of the transfer unit is a measure of the separation effectiveness. So the smaller the height of the transfer unit, the more efficient the removal. So what I'd like to do is go through a couple of examples today. The first looks at the use of breakthrough data for a test column for evaluation of a full-scale column. So we start with a situation where we have the total organic carbon, and that is 200 milligrams per liter. So we have this phenolic wastewater, has total organic carbon, and we're going to treat that through a fixed bed GAC column, and we have a wastewater flow rate of 1,000 liters per day. The allowable effluent concentration is 10 milligrams per liter, which corresponds to 5% of the initial TOC. And from the breakthrough curve, we obtain the following data. The volume that we can treat to breakthrough is 2,080 liters, and the volume we can treat to exhaustion, which we've defined as 95% of the initial concentration, is 2,930 liters. A full-scale adsorption column is designed to be 1.6 meters diameter, 6.1 meters in height, and containing 1,560 kilograms of carbon. And you're asked to use that information to determine the height of the adsorption zone, so that's Z sub S. We'll also determine the number of transfer units, and we will determine the time to breakthrough. Let's proceed with this. So the information we have is C naught is equal to 200 milligrams per liter. C at breakthrough is equal to 10 milligrams per liter. Q for the wastewater is 10,000 liters per day. We have a test column that contains 3 kilograms of carbon, and we've been told VB is equal to 2,080 liters. So this is just the information from the previous slide at 5% of C naught, and BT is equal to 2,930 liters at 95%. So we'll look first at the test column. I'll use the VB hat to distinguish between the volume that we have at in the test column and the volume we have in the design column. So VB is the volume that we treat per kilogram of carbon to breakthrough. Okay. So we have 2,080 liters, and we have 3 kilograms of carbon, and that is 693 liters of water that we can treat per kilogram of GAC. V hat T is the volume that we treat per kilogram of carbon to exhaustion, and that is 977 liters. So that's, we can treat 977 liters of water per kilogram of GAC, and that's to exhaustion. So for the design column, which was 1.6 meters in diameter, 6.5 meters in height, and contained 1,560 kilograms of GAC. So here, VB is equal to the 693 liters per kilogram of GAC times the mass of GAC we have in our design column, and that is equal to 1,056,000 liters, or 1,056 meters cubed. So this is the amount of water treated to breakthrough. V sub T is 977 liters per kilogram of GAC times the 1,560 kilograms, and that is equal to 1,523,600 liters, or 1,523 or 24 meters cubed. So that's the volume of water that we can treat to exhaustion. Z sub S is equal to Z, the height of our column, times V sub Z over VT minus 0.5 V sub Z, and I did not derive that equation, and you can. The textbook does not just derive it either. Much of this actually comes out of the secondary textbook, which is also available through the MSU library system electronically. So that's 6.5 meters times V sub Z is equal to V, let's just write this here, VC is equal to VT minus VB. So just remembering that relationship. So that's 1524 minus 1056 divided by 1524 minus 0.5 times the difference between those two. I apologize, scrunching this together here. And for all of the lines and that is equal to 2.36 meters. So that is the height of the adsorption zone, which corresponds to a height of a transfer unit. The number of transfer units is equal to 6.5 meters divided by 2.36, or 2.76. So note that the height of the column, or Z, is equal to the height of the transfer unit times the number of transfer units. And the time to breakthrough can treat 1,056 cubic meters. We divide that by the flow rate, which is 10 cubic meters per day. So that's volume to breakthrough divided by Q. That's our time to breakthrough, and that is 106 days. So that would mean that roughly 3 times a year, you would need to either remove the GAC or regenerate the GAC in place. Questions about this approach?
So that number of transfer units is like, it's like how many of those 2.36 meter like distances, I guess you would have like in one, or is that like an actual? Okay.
So let's just, here, let's go here. If this is the column here, so this is the height of the column here. And when we talk about the transfer units, if I had a sampling port here, so this would be the height of a transfer units. This concentration right here would equal my exhaustion. So basically, what's happening is you have equilibrium essentially in that height. And then what's going to happen is that height, that zone, moves down the column over time. So then over some next period of time, you'd measure. Now you've exhausted this portion. You've exhausted this portion of the column, of this portion here. And why is it not changing back to red? Okay, so you've exhausted this portion, and that moves down. Then you exhaust this portion here, and your adsorption zone moves down the column until you get to the point where the concentration leaving the column is 95% of what's entering the column. I don't know if that helps in terms of, and the number of, so this is the height of the transfer unit, and then the number of transfer units are the number of these adsorption zones you have in the column. So if you have, for instance, if my height of my transfer unit is very large, what that means is that I don't have very efficient removal. In order to achieve that same level of removal, I need a much taller column. So in this column, I'll get much more efficient removal than I will in the column on the right. In order to get the same level of removal, I have to have a much taller column. So what you really want is as small a height of a transfer unit as you can achieve. That's an efficient column.
So we're doing, excuse me.
It's also more difficult to regenerate, but it's a more efficient removal.
Okay, so we're doing this with granular activated carbon right now. Can you do this with the powdered version too, or is that just pretty much strictly added like with coagulants usually?
The reason you don't have a column with powdered activated carbon is because of back pressure. The porosity is too small, and it takes too much pressure to basically push the water through the column. So kind of think about the difference between if you have, here's your surface, and you dig a hole, and this is in clay. And you dig a hole, and this is in sand. Which can you will water flow through faster?
Be the sand.
The sand,
Larger
okay?
grains.
And think too then at, for instance, back at the filtration. If instead we have, this is coarse sand, and this is fine sand, when we did those head loss calculations, how was head loss affected by the diameter of the particle?
Wasn't it increasing with smaller diameter?
Exactly. Okay. And it also increased with porosity to the fourth power. So it was inversely proportional to porosity. So as porosity decreases, which it will as we move to fine sand, it's going to increase to the fourth power. And it increased to the square of the diameter of your particles. So the smaller the particle, the greater the head loss. So if I go to powdered activated carbon, which is a really small particle size, I'm going to have a very high head loss, which means I have high pressures in order to push the water through that column. So you'll never see a column with powdered activated carbon. You'll only see powdered activated carbon added either as a batch or a continuous system, for instance, is adding it with the coagulant. Does that help?
Yeah, so for the granular, is there like an optimum like grain size we're looking for?
Typically, it's about the grain size of a medium grain sand. Kind of think of it that way. The larger you get, the longer it takes typically to reach equilibrium, because the less surface area. Here's your grain size. You've got a stagnant layer here, and your pollutants have to diffuse through that stagnant layer. So this is the particle. If we make it same mass, but we make it smaller, we have more surface area for diffusion. This part. So typically what I've seen is it's kind of a balance between head loss and the rate at which you achieve equilibrium. It's about 40 mesh is about what often is used. Forget exactly how that correlates to grains to the actual size, but mesh sizes are the same. The granular activated carbon that we used for filtration. Any other questions about this? Because it's a really good question in terms of, why do we use granular activated carbon? Why not use powdered in a column? It really has to do with operation. And you can see the hydraulics are the same for GAC as they are for sand that we use for filtration. The exact same equations, exact same property. Other questions?
I guess just like a general overarching question. So we talk about head loss a lot, which I guess makes sense to me. I feel like if you minimize the head loss throughout the entire plant as a whole, wouldn't that like save you in terms of costs for energy and stuff?
Exactly right. So if you can operate a plant with gravity, then that saves you in pumping. The greater the head loss throughout your system, the more pumping you're going to have to do, and the more costly it is to operate, simply because of energy costs. I haven't done it here. In any plant, you would do a energy grade line and a hydraulic grade line for that plant in order to determine the head loss through the plant and determine whether you need pumping. So for instance, and it's hard to visualize because we don't get to see it, but the flow of water through a plant is often by gravity. If you can lay out the units to actually allow water to flow by gravity, that's far better than it is to have to pump. I used to make students do the hydraulic grade lines and the energy grade lines in the design. I haven't done that in recent years, but it's important to consider that you would never design a plant without actually creating a hydraulic grade line and an energy grade line for that plant flow, for the water flow through the plant. So extremely important consideration. Let's look at this next problem. Similar problem, but some different terms are introduced here. So again, think here, we have a column, we monitor the concentration in the effluent versus the volume we treated, and we have a breakthrough curve that looks something like this. So if this is the concentration at breakthrough, this is C naught. This corresponds to the mass of contaminant that I can remove during treatment. So this is approximately equal to Q times the concentration in the effluent times the time to breakthrough. And that is approximately equal to the mass of the media times X over M C influent. So the X over M value at the influent concentration. So in this case, again, we have a adsorption column. This is used to remove microcystin, which is an exotoxin produced by blue-green algae. It is what shut down the Toledo plant about 4 years ago. It shut it down for 3 days because of the microcystin concentrations in the raw water. So the column has a diameter of 3 meters, depth of 2.5 meters. It's treating a flow of 2,540 cubic meters per day. Source water has 1 milligram per liter. Our breakthrough concentration is 0.001 milligrams per liter, and that's based on I forgot to change this. This is actually the term, it's the MCL. MAV is maximum allowable value, and it's what's used in New Zealand. And I didn't realize that I hadn't changed that. And the bed has a density of 450 kilograms per meter cubed. So we're going to go through and we're going to look at a number of terms that are typically used with adsorption. So we have a diameter equal to 3 meters. We have a depth of 2.5 meters. We have a bed density of 450 kilograms per meter cubed. We have a flow rate of 2,540 cubic meters per day. And C0 is equal to 1 milligram per liter, and C breakthrough in this case is 0.001 milligram per liter. So the first thing we need to do is calculate the cross-sectional area, and that is just pi over 4 d squared. So that is pi over 4, 3 squared. And that is 7.07 meters squared. The volume of carbon in this bed, or the volume really of bed is what it is, okay, is equal to the area times the depth, and that is 7.07 meters squared times 2.5 meters. And so this is the volume in my column. So here's my column. The volume of carbon in this column is 17.7 cubic meters. The empty bed contact time is the volume of the bed divided by your flow rate, and that is 17.7 cubic meters divided by the flow rate, and we'll calculate this in minutes, and that is 10 minutes. And the typical range is 5 to 60 minutes. That's a typical range for empty bed contact time. The next term that's often used is what's referred to as the superficial velocity or the surface loading rate. This is not the velocity of the adsorption zone. Okay. This is simply Q over the cross-sectional area. So it is the 2,540 cubic meters per day divided by the cross-sectional area. And typically this is in hours. So we'll divide the flow rate by 24, and that is 15 meters per hour. And typical range, I'll just give you the typical ranges in a box to this, is 5 to 15 meters per hour. So it's on the high end, but it's within the range. The service flow rate, denoted as SFR, is Q divided by the volume, and that is our flow rate divided by the volume in the reactor. And again, typically this is in hours, and that is 6 meters cubed per hour per meter cubed. This then is typically reported as bed volumes. So it's typically reported as 6 bed volumes per hour. And that's typically the way you'll see this service flow rate reported for a GAC. You'll also, when we talk about ion exchange, you'll see it's also used for ion exchange. And the typical range is 1 to 12 bed volumes per hour. The maximum specific throughput is denoted as VSP max, and that is equal to X over M C influent divided by C. So we need X over M, and we'll use a Freundlich isotherm, and this data would need to be given to you. So we'll use data for microcystin. So that would be 59.9 times 1.0 milligrams per liter to 0.48. This would have to be provided for you on the homework problem. The Freundlich parameters are provided. And this is equal to 55.5 divided by, and this is milligrams per gram, divided by 1 milligram per liter. So one needs to know, they need to specify the unit. And this then says that we can treat 55.9 liters of water per gram of GAC. So that's what we can treat, or 55.9 meters cubed of water per kilogram of GAC. The carbon usage rate, CUR is the acronym used for that, is 1 over VSP max. So it's, apologize for all these lines. 1 over the maximum specific throughput. So that is equal to 1 over 55.9 meters cubed per kilogram, or 0.018 kilograms of GAC per meter cubed of water treated. The volume of water that we treat is equal to VSP. Notice this is a max, because we haven't taken into account what's in the effluent. Okay. So that's why it's a maximum specific throughput times the mass of carbon, and that is equal to VSP max times your bed density times the volume of the bed. So that is 55.9 meters cubed per kilogram times 450 kilograms of GAC per meter cubed. This is GAC times the volume, and that is 4.5 times 10 to the 5 meters cubed. So the maximum volume that we could treat through this column would be 4.5 times 10 to the 5 cubic meters. And the last thing is the bed volume, and that, is the bed life. So how long before you have to regenerate? And that is equal to this volume that we can treat divided by Q. So it's 4.5 times 10 to the 5 cubic meters divided by our flow rate, and that is 175 days. So that is the absolute maximum. At least at every 175 days, we would need to regenerate or replace the carbon. This assumes no competition. If we had competition between the microcystin and other contaminants, how would all this be affected?
Would your bed life go down?
Your bed life would go down dramatically. So we look here. If this is our breakthrough, normally, typically, if you have competition, you're going to see a breakthrough that looks more like this. So it's not going to be as sharp of a breakthrough. And this is CB, you see you're going to actually use much less of the column. So if you think at the talk that Mike Ellis gave, they had a first column, and then they had a second column. So the first column, they were using carbon that had been regenerated. And the second column was their polishing step. What they were doing in the first column was recognizing that they had other contaminants, just even natural occurring organic matter, that would consume sites on the carbon. So they were trying to remove that with that first column and then use the second column to really lower the PFAS chemicals, the PFOA and the PFAS, down to the levels that they needed, PFOS, down to the levels that they needed. So you can sometimes operate a system like that. The carbon that they were using, because it's difficult to remove the PFAS compounds, that's expensive. So you want to protect that column. So that first column essentially protects your polishing step and your second column. Other questions? No other questions? We will end there.